Hello, how's it going? Hello? How's it going? Greetings, it looks like people are getting on. Hello, is everybody able to see the screen?
Yeah.
Yeah.
Okay. So this is the last of our 5 meetings. And so what I want to do today is I want to finish going over some of the error detection, error correction theory, give an example, and then arrange to have a one-on-one session with each one of you. And so we're supposed to have our calendars out and try to find a time that works. And then from this point onward, then there's lots of different ways to generalize and start doing original research amongst ourselves. And so we'll then brainstorm about a couple of problems. I've got some suggestions. So let's just quickly recap where we were from last time. So I've put up the final image where we have cubes. And if you remember, it took us a long time to see how many planes there were and how many check digits there were and how things were able to perfectly align and specify if there was an error, where the error was. And since things can only be a 0 or 1, as soon as we know the location of an error, we know how to fix it. So the more times you do algebra, the easier it starts to get to just look at something and see how to simplify it. I was working on an interesting problem with one of my students, and it involved a lot of factorials and pulling things out and expanding. And I had enough experience that I knew how to approach it. And at the end of the day, the terrible expression simplifies to 1 over the square root of v in the limit. A really nice number. And so we want to get to the point of we can often do better than we were doing in 2 dimensions. We get a percentage for large n that is better than what we're getting in 2 dimensions. Now, there's other things you can do. So we're going to spend a lot of time now talking about Hamming codes. And we're going to just do the 7-4. There's a lot of different generalizations. Another way you can go, which we're not going to spend too much time on, but you should at least be aware of it, is that there are ways to send messages where you can correct 2 errors or 3 errors. And so one of them is a great one. It's called the Golay code, where you send 24 bits, 12 of data, so it's 50%. It at least hits the 50% mark, but you can correct any 3-bit errors as well as some others. So I've just given you some links in case you find something like this interesting. So I want to talk a little bit now about Hamming codes. So if you look at let me try to keep this here. I'm trying to just block things off. Just give me 1 second. Okay, so if you look at this, I have a chart, I have a graph with just 7 points. And for those 7 points, I know it's been a while since we've looked at the stuff. We were using red before for data and blue for the error detection and correction for the, the check digit. And so now what I'm going to do is I'm going to use different colors for the check digit. I'm not going to use just blue, but I want to use different colors to help make it easier to keep track of what's going on. And so we have 4 bits of data out of 7 if this works. So that breaks the 50%, which is what we wanted. This is better than what we were doing with the square and the triangle. With the triangle, the best we had, for small values was we had a message with 6 bits, with 3 bits were data and 3 were check. Or if we did the 2x2 square, we had 8 bits of message with 4 being data. So this one is 7 bits, so it's between the 6 and the 8, and 4 bits, or a majority, about 57%, is going to be data. So the claim is that this is going to correct any 1-bit error. Now, if you look at it, the points are labeled in a very strange way. So I've got D1, D2, D3, D4 as the labels up top, data 1, data 2, data 3, data 4. And then I've got my check digits, my points 1, 2, and 3 down below. But I've given them the numbers 3, 5, 6, 7 up top and 1, 2, 4 down below. Any guesses why they're numbered 1, 2, 4 down below?
It's different powers of 2.
Excellent. It's different powers of 2. So if we were to go up a little bit higher, the next point below would be what point?
8.
Probably would be 8. And how many points do you think we would have if we went up to 8?
Four. Oh, wait. Is it 11?
So why 11?
Because 1 to 15, there's 15, and then 1, 2, 4, 8. You do 15 minus 4, it's 11.
That, if we go up to a power of 2, then the number of total points looks like it's 1 less than that. So we would have 15 points, and since 4 of them would be check digits, that would mean 11 of them would be data. And again, you could only had 2 digits. How many points total do you think we should have in that case? So this is the case with 3 check digits. If we only had 2 check digits, how many points do you expect we would have overall?
Three.
Yeah, 3. With 3 check digits, the points are 1, 2, 4. So we go all the way up to 7, which is 1 less than 8, 1 less than the next power. We just guessed a moment ago that if we had 4 check digits, they would be 1, 2, 4, and 8. So we would go up to 1, 2, 1 less than 4 is 3. So if we have 2 check digits and 3 rules. So it seems like this could be a nice generalization of the majority rules. So again, you always want to try to find a way to put what you're doing in context with other stuff you've seen. And this appears to be one way to do that. So going backwards doesn't seem so bad. And now the question is going forward. what do we think the next one would be? Well, before we can even figure out how to add all points, we should at least make sure that this works and it does what it claims to do. So this is supposed to be able to detect and correct any error. I'm naming this after the Manhattan subway system. We have all these different lines for the subways. And so we have similar to what we did before, the check digit sums all the things that's mod to be a multiple of 2. And so, for instance, the blue line goes to points 3, 5, and 7. So 3 plus 5 plus 7 plus 1, whatever those values are, has to be a multiple of 2. If it's not a multiple of 2, you know one of those is wrong. So let's go through this carefully and show why it works. So imagine that there's an error in the blue line. Well, let's first say that that there are no errors. If there are no errors, then everything is correct and life is good. All right, now let's imagine that only one color has an error. So imagine that the only error is in the blue. If the only error is in the blue, then the error has to be just P1. If the only error is in the orange, it has to be P2. If the only error is in the green, it has to be P3. And the reason is if there was an error, say, in point D1 up here and point 3, then that error would be detected by both the blue and the orange. So because we're only detecting one color as wrong, it's going to be the check digit that's wrong. Any questions about that?
No.
Okay. So now, let's imagine blue and orange are wrong. So I claim that if blue and orange are wrong, the only point it can be is D1. So can somebody tell me why it has to be D1?
Because it is the point they share.
So is there any other point that blue and orange share other than D1?
I think D4.
Yes, so why couldn't it be D4?
Because it's also sharing it with green.
Good, it's also sharing it with green. So if D4 was wrong, then blue would have an error, orange would have an error, and green would have an error. So because blue is wrong, we know it's either 3, 5, 7, or 1. Because orange is wrong, we know it's either 3, 7, or 2. So now the 2 points that are still alive are 3 and 7. But because green is correct, we know that 5, 6, 7, and 4 are correct. And so it has to be point 1. Similarly, if blue and green are both wrong and orange is correct, well, what do blue and green both go to? They both go to 5 and they both go to 7. But orange also goes to 7. And since orange is correct, then that means point 7 can't be wrong, so it's going to be point 5, the data point 2. Similarly, if orange and green are wrong, what do orange and green both go to? They both go to point 6 and 7, but blue also goes to 7, and since blue is right, that means point 7 has to be right, wrong. And the last, imagine blue, orange, and green are. And so because of that, we would have that the data point 4 is wrong. So this is an extremely powerful approach. State really the problem number. And I say I want to transmit n bits. Correct. At most 1 hour. What is the best 2 hours? Now, when you're actually doing things, you might find this configuration with 7 points that's better. 6 points with the triangle was 50%. 8 points with the square was 50%. 7 points, well, that's giving us, I think, 57% efficiency. Yeah, 57% is data. So if we go back, we'll figure out how should we put points. Putting points down spaces. We might want to work in a 20-dimensional space. It's hard to visualize something like that. So at some point, you have to start thinking about cubes. So instead of using a cube, what might be another good shape to use? So there should be some advantages to a cube. Let's go back to the square numbers. Are people able to hear me? Can people hear me?
Yes.
Yeah.
Okay. Okay, so can somebody give me a thought? Which do you prefer? Do you prefer working with the triangle numbers, or do you prefer working with the square numbers? Which do you think is easier to work with? Yeah, what each digit is going to be harder to figure out how to put them on. So in terms of implementing the code, the square numbers are easier. Which is better though, the square numbers or the triangle numbers?
I guess I think that the triangle numbers, because it has fewer data points. But the
fewer data points. You're close. It has fewer points overall, but it has the same efficiency. So you're more likely to have 2 errors with the square than 2 errors with the triangle numbers, because the square is just more points. So there is an advantage to the triangle numbers over the square. The triangle numbers give you the same level of efficiency, the same percentage of your message's data as the square numbers, and they do it with fewer data points. And they do it with fewer points overall. So fewer data points and fewer check digits. So you're less likely to have two errors with the triangle numbers and the squares. So because of this, there is an advantage to using the triangle numbers. The square numbers are much easier to code. Now, when we look at the percentages, let's do a comparison. Let's say we want to transmit around 2 to the 12th or 4,096 bits of data. So we could do a square and a cube. And then I've written down what the corresponding Hamming code would be. The square is going to have 4,096 bits of data. It'll be 2 to the 6 by 2 to the 6 out of 4,224 when you add in the check digits. So it's a good exercise to just go through and check all these numbers. So you get an efficiency of 96.9697%. If you do the cube, well, this is why I chose 2 to the 12th, because 2 to the 12th is 2 to the 6th times 2 to the 6th. It's also 2 to the 4th times 2 to the 4th times 2 to the 4th. So when you look at the cube, you could have 4,096 bits of data out of 4,144 bits overall that you're transmitting, for an efficiency of 98.8417%. And if you use the corresponding Hamming code, you get 4,083 bits of data out of 4,095 pieces of information for an efficiency of 99.707%. So when you start using very large sizes, the efficiency is almost 100%. Now, you have a greater chance of having 2 errors, but we'll ignore that for now. We'll assume that there's still only 1 error. Of these 3 percentages, clearly the Hamming code is doing best. But the other ones are still pretty good numbers, roughly 97% and roughly 99%. So sometimes you might be willing to sacrifice a small amount of efficiency for ease of programming. I might not sacrifice 20%, but if I'm within a percentage point, well, that might be close enough that I would just rather have something easy to code. Now, if you're doing any industrial application, you often bite the bullet and spend the time coding it well because you only have to code it once. I've been told that the way CDs work is they basically read each bit of information 16 times. Now, this is extremely wasteful to read things 16 times, but they can afford to do this because it reads it so fast relative to how it has to process the data that it can afford to take this time. So when we have large things like this, there's small benefits of Hamming over cube, there's benefits of cube over square. But instead of looking at a cube, what other two-dimensional shape might you want to look at?
Triangle?
Yeah, except it's not going to be a triangle in higher dimensions. What would a triangle be in 3 dimensions?
Triangle.
Pyramid.
A pyramid or a tetrahedron. So one project is to try to look at what would happen if we had a tetrahedron. And for each tetrahedron, try to imagine what would its efficiency be. And then compare the tetrahedra to the cubes here. You could also look at other platonic solids. There are 5 platonic solids. For each one of these, you could try to calculate what is going to be the efficiency and try to build a code along the platonic solids. When you go into higher dimensions, then it becomes an interesting question, what kind of nice solids do you have? What would you want to do in 4 dimensions? So one thing that can be done is for each integer n, let's say we want to transmit n bits of data, what's the best arrangement we can do? So we saw that there is, there's the tell me 3 times, and then, that becomes the start of our triangle numbers. And then the next one is, we have 6. And when we have 6, we have 3 bits of information. Or we have 8, where we have 4 bits of information. So both of them are 50%. It turns out that 7, we can actually do better with 7 than we can with either 6 or 8. But we've never said anything about 5. Is there something good to do with 5? What's the next triangle number after 6?
No.
10.
It'll be 10. And what's the next square? Next square is going to be 16. Sorry. The next square I guess we'll have is 9 points, and then we got another 6, we get 15. So we have, for the next triangle number, 10 data points, where 6 of them are checked. 4 of them are checked digits, 6 of them are data for 60%. Or we have the 3 by 3 square, which when we add our check digits, gets us 15 points to transmit, where 9 of them is data. So here we have 10 points, here we have 15. We haven't said anything about 11, 12, 13, or 14. If I give you those, what's the best configuration you can do? Now, we haven't proven what the generalizations are for the Hamming codes. But from what you were saying, you were guessing that if we added 1 more check digit to go up to 8, we would have 15 points to transmit. And you would have 11 pieces of information out of 15. That's better than the square. So there could be more than one natural candidate from a given number of points to transmit. And it may not be immediately clear which is going to be the best, which is going to be the most efficient. So, we have a lot of you in this class, which is wonderful. There's a lot of cases to look at. And so you need to decide, and you need to talk amongst yourselves and talk with me, what do you want to pursue? So you have all chosen an extremely ambitious project, cryptography. This is one of the most important subjects in 20th century, 21st century mathematics. A lot of people have looked at stuff like this. So for me, what I want you to get out of this is I want you to get out of this how to think about new problems, how to come up with things to try and attack. And it would be wonderful if we come up with something new. It's extremely hard to come up with something new in cryptography using elementary techniques just because this is such an important subject. So many things have already been done. So one of the things we can think about is what are different efficient ways to construct things. And then the tweaks we can do is we can try to do things so that we can correct 1 error, or maybe correct 2 errors, or maybe correct 3 errors, and see how that changes the geometry. What's nice about this is in terms of the background material we need, it's extremely minimal. You don't need advanced probability. You don't need advanced linear algebra. You don't need calculus. You need to find clever ways to connect points with check digits. Maybe you use more exotic curves. Maybe you use higher dimensions. You need ways to specify where things are. So what you need to do is you need to decide what do you want to look at. And then we'll all talk amongst each other. Okay. Any questions on the type of project that we're going to be doing now?
No.
Okay.
I have a problem actually. Like,
yes.
Would a project be divided into like separate parts for everyone to solve?
Well, so one of the things is, different people can choose different numbers of points to transmit. Some people can choose to look at having a system that detects and corrects exactly 1 error, while other people might want to look at detecting and correcting 2 errors. Some people might want to say, what's the best configuration I can have staying in a plane? Other people might want to explore higher geometries. So there's lots of different approaches you can try. And what's nice is you can talk amongst yourselves. When I have summer research students, they spend 40 to 60 hours a week for 9 or 10 weeks in the summer working closely with me and each other. That's a lot of hours. Most of you I know are doing lots of other things this summer, which is wonderful, but it means you have less time to do things. So the advantage of being able to have so many of you working on this problem is you can actually split it up and have different people looking at different things, but using similar techniques, and then you can get back together and compare notes.
Okay, thank you.
Does that help explain? Yeah, so we're very fortunate that we have so many people looking at this. It's also quite easy to make errors in calculations. And so when you have another set of eyes to look at things, this is wonderful. Now let's just look at this picture for a while. There's only 7 dots. So one question I could ask you is, how many ways can I connect the 7 dots? Well, I'm probably not going to have check digits connected with each other. So you can view this as what's called a bipartite graph. Nothing on the top is connected to the top. Nothing on the bottom is connected to the bottom. And so you can only have edges from top to bottom. So one question is, how many bipartite graphs can you have on 7 vertices with 4 up top and 3 down below? So one possibility is we could have, for every point down below, it could be connected to every point up above. Here, every point down below is connected to exactly 3 points above, and no 2 things are connected to the same. So if there aren't that many possibilities, can you just go through all of them by brute force? Can you write a computer program to go through them? Or can you break it up into a bunch of cases? You know, what if you wanted to have 5 points upstairs and 3 points down below? Could we do something like that? Again, it's probably going to be very hard to beat what Hamming and others did. We haven't talked about why Hamming came to this. We've just shown that it works. But my question is, you know, there's a deep reason why, and it is related to some things with powers of 2. Wikipedia has a nice entry on this. But could we have experimentally discovered this if we just tried to play with ways to connect things? And so what you can start to do is try to play similar games. What if you have 9 data points? What if you have 9 points that you're transmitting and you want 5 or 6 to be information? Is there a good way to do that? Is there an efficient way to go through all possibilities? When we're using things like the cubes, it's clear how much information we're going to have. Can you get a similar result for the tetrahedron? How easy is that to encode? What if you use, you know, something where the sides are pentagons? So there's a huge number of questions you can ask. And you know, again, you have chosen an extremely challenging project. You have a tremendous amount of bravery to be trying to do original research in cryptography in high school. any world power spends billions of dollars a year on cryptography. Plus you have all the companies that are heavily invested in stuff like this. Most of the low-lying fruit has been picked clean in this subject. And this is the disadvantage of working in a field like cryptography. If we worked in other areas like number theory, there's a lot of elementary problems you can look at that are related to other things that just, they're interesting, but nobody has really looked at them before. For cryptography, most of these things have been studied. But occasionally, there might be an opportunity. Maybe somebody has been more concerned with a certain application, and so they haven't pursued something. Maybe they're so happy with the Hamming codes and the Golay codes, they didn't look to see what else could you be doing. And so there's a good chance that at the end of the day, we will not find anything that beats the existing algorithms. But we could maybe get some results about how well the pyramid numbers work. Or what does the pyramid become in even higher dimensions? We have some results about how good the cube codes are. It's n squared over n plus 3, or n squared over n squared plus 3. That's much better than n over n plus 2, which is what we got for the square numbers. So one question could be, if you want to look at what goes on in the limit as n goes to infinity, in the plane, if you use squares, you have an efficiency of n over n plus 2. In 3 space, if you use cubes, you have an efficiency of n squared over n squared plus 3. That's a little bit better. What happens if you go to higher and higher? What do you get in d dimensions? Okay. Any other questions about this?
Yes, Professor. So I was wondering whether the geometric configurations is necessary when considering the probability. Like, is there an kind of asymptotic formula for the best you can achieve?
I have no idea what the best formula is. I know what the formulas are for Hamming codes, and the Hamming code formulas is beating the cube and the square. But maybe I doubt it, but maybe there's a geometry that does better than Hamming. But it might just be interesting to see if you don't have that perfect power of 2, if you have fewer data points, what's the best you can do? The Hamming code, you have to have something related to a nice power of 2. What if we don't have one of those numbers? What's the best code you can do where you transmit 11 pieces of information? And your Hamming might tell you, well, you don't want to transmit 11 pieces of information. You want to transmit either 7 or 15. But maybe we have 11 to transmit. And it just might be interesting to know what is the best code you can do for detecting one error if you transmit 11 pieces of information. And that might be open. So one of the things you all need to do is do a little bit of research on the internet and see what has been studied, what is known, what's unknown. But these are all good questions. There's a lot of freedom in terms of what you study.
Okay, thank you very much.
Yep, you're welcome.
And by the way, Professor Miller, you mentioned higher dimensions, but how can we visualize that?
So there are some tricks you can do for higher dimensions. So everybody can picture 3 dimensions. What some people do is they do a color to represent a 4th dimension. So maybe red would be very high, blue would be very low. Or maybe what you might do is you might picture, to try to picture 6 dimensions, you might picture 3 dimensions and then at every point in 3 dimensions, you might have a sphere, and it gives you another 3 dimensions. It is very hard to picture higher dimensions. And so at some point, you have to lose trying to draw your intuition by physically drawing the object and staring at it and looking at the object just more abstractly. Well, you can't quite see, an 8-dimensional cube. I think you can see how to do the calculation. And so those are things to try, but I agree with you that it's going to be difficult to just view that stuff. Other questions?
So Professor Miller, what if the method that we discovered can't be what if it isn't a geometric shape? It's just a bunch of subsets.
That's fine. It doesn't have to be a geometric shape.
Okay.
Geometric shapes have the advantage in that it's very easy to describe what you're doing. So for these shapes, it's very easy to explain how I'm choosing my code, how I'm choosing my check digits. There is a way to explain what's going on with Hamming, and you can read the Wikipedia article in terms of why these are the ones that are connected. Why is 1 connected with 3, 5, and 7? Why is 2 connected with 3, 6, and 7? But it doesn't have to be geometric. Anything you want is fair game.
Okay, thank you.
Yep, you're welcome.
Yeah.
So there's a tremendous amount of freedom. And you are at the stage of your lives where what's more important than getting a result is getting some familiarity with how do you do research? How do you gather data? How do you write things up? How do you present it well? How do you do a literature review? How do you look and see what's been done? And again, this is a tremendously difficult subject to do work on. It's a very interesting subject. And a lot of the current work on it uses an enormous amount of mathematical sophistication. Advanced graduate level mathematics. We're not going to be able to do that in the summer. So the question is, what can we do with simple counting and combinatorics and whatnot? So the problems here are related to things that people care about, but it's more designed for problems that we can look at. Oh wait, something's missing. Give me 1 second. So I want to just load up one last thing. Okay. So I want to look at one last thing before we do the steganography. So imagine you want to transmit a string of numbers. So 0 1 1 1 1 0 1 0 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 something like this. Okay? Now we have codes, and we've been spending a lot of time on this, that talk about how do you correct and detect errors. And we can correct or detect 1-bit error, which is great. But if there's more than one bit error, we're in trouble. And so the problem is, imagine there's a localized burst of noise, and the digits that are in red, we're going to receive them incorrectly. So it's supposed to be 1010, we'll get 0110. So this one will be correct, and the other ones will be wrong. Okay? Because this burst of noise is localized, there will be one segment of the message where I'm going to have a lot of errors. And then our code is going to be useless. Our code requires that there's only one error. We now have 3. So the question is, how do you handle something like this? And there's a beautiful solution called interleaving. And so while we may not be able to prove a lot of original stuff this summer due to the difficulty of the challenge, we can at least see a lot of really clever ideas. And we can see that these problems can be solved without using advanced machinery. So there is the possibility of just having a great observation, of just looking at things the right way. And here's how it works. So do we all agree that what's really bad is these errors are all close to each other? And because they're so close to each other, things break down. So what we do is we transmit and send just maybe every 4th number. So if we transmit every 4th, here's the first, the first number, the 5th number, the 9th number, etc. The 2nd number, the 6th number, the 10th number, etc. And when we do that, now you see the red digits have been switched, and now they're in different messages. And now each one of these, the localized burst of noise, has been split among 4 different strings. And in practice, you would want to use a number larger than 4. You might use 100 or 1,000. So there's a disadvantage to this method. It means we have to take what we're doing and we have to split the message up. So this requires us to know the whole message in advance. We can't just transmit digit by digit as they come in, but that's not a big deal. And the wonderful advantage we get is that we are able to split the effect of a burst of noise into multiple distinct strings so that no string has 2 errors with high probability. And thus we can now survive a burst of noise, which before would have taken out our message. So to me, this is the essence of great cryptography. A small, clever idea which allows you to do something tremendous. So any questions about this? Okay, so this just shows you it is possible to solve a major problem using very elementary mathematics. It's hard to do, but it is possible. Oops. Okay, so now here's the last bit, steganography. So steganography is the art of hiding an image in another image. So does everybody see the pretty trees with the sky? This should not be a hard problem. Everybody sees the trees in the sky. I know you've got stuff on mute. I'll assume you all see the trees in the sky. Can anybody see the cat that's hiding in the trees?
Professor Miller, the screen is still on the interleaving.
Yeah, we can't see the tree.
It's still on the interleaving?
Yeah.
All right, let me try again. How about now?
Yeah.
Yeah.
Okay. Interesting. On my end, it said it was sharing the screens. Okay. So now can everybody see the tree with the sky behind it?
Yeah.
Yeah.
Yes.
Can anybody see the giant cat? And it's a huge cat in the trees.
No.
Okay, so I am going to show you where the cat is in a few moments. The cat is hiding in the tree. And so I want to talk to you a little bit about how messages are transmitted and to give you some sense about why we care so much about these error correction, error protection codes. Okay. So how do you transmit an image? So imagine you have an L by W grid. So the grid is going to have L times W pixels. Those are going to be the individual little squares. And typically, each pixel is going to be a triple of colors, often red, green, blue. There's another triple you can do using cyan, but let's do the red, green, blue. Because computers love base 2, we typically do something maybe like 256 choices for each color. So red might run from 0 to 255. Well, if there's 256 choices for each, and we have 256 cubed choices for each triple, or 16,777,216 possibilities. That's a lot of colors that we can transmit. When you think about the power of the human eye, there's only so much we can discern. There's only so much we can distinguish. This is why for a lot of things involving CDs, they're already better than the human ear can detect. We don't need to make them better. So if I want to send a message, one possibility is I just send the red, green, blue triple for every point in the grid. All right. And now let's talk about steganography, which is concealing a message in another message. So let's take one of the colors red. And let's say the numbers go from 0 to 255. So we've already talked about writing things in binary. Right? We did RSA earlier. And so if I want to write things in binary, I have digits R0 through R7. So I'll have R7 times 2 to the 7, which is 128, plus R6 times 2 to the 6, which is 64, and so on and so on and so on. So imagine I change just the last digit R0, or maybe the last two digits R1 and R0. I'm not going to change my number by a huge amount. It's going to be very hard to see the difference in the image. And in fact, depending on how I want to change them, I might see that no change was needed at all. So this is how we can hide an image in another. So for instance, let's say I only change R0, and I have another message which might be a text document with some writing on it. And so I can have a white background and black text. So each pixel is either going to be 0 for white or 1 for black. So I can change R0 so that now, instead of being the thing I needed for my image, it's now whatever I need for this black and white image. And the hope is that some of the times when I need to change R0 to, well, it was already that anyway, so that the color won't change. And in the places where I do have to change it, I'm only changing the color by one number out of 255. 1 out of 100 is 1%. We're talking about a 0.5% change in the red tint. That's not that significant. And we can use this to hide a white image very easily, a white and black image very easily. So here's the tree. If we just do this to like the last digit or two, there's the image of the cat. You can have a slightly low resolution image of the cat. You can see it's a little fuzzy. You don't have all these great sharpnesses, but you can hide that inside the main image. Absolutely wonderful. Okay. Any questions about this?
Yeah, I have a question. So
Yes.
when would you actually use this, or how is it used like currently in like the industry?
I don't want to say too much about how it's used. I'll just give one example. Imagine you want to leave a message for somebody. You can modify an image, have the image posted, and then anybody who goes online and sees it, if they know how to decode it, they can find the message. So unfortunately, this gives ways for people to leave messages without having to advertise who the message is coming from. A lot of times you can look at communication patterns between various individuals. You don't want to do things like that. You don't want to get alerted on somebody's radar screen. So I don't say too much more about stuff like this. You can do some searching, but there's a lot of applications. And then, of course, one of the big questions is, how can you tell if an image has been modified? Are there tests you can do? It's kind of stupid if all you do is modify the last digit. So, if you don't want to do the error correcting, error detecting, one thing is to try to come up with a project related to this. What if is there a nice way you can come up with to modify the last digits or the last digits to hide messages, and to do it in such a way as to avoid detection? Tests can be run to see if you've doctored an image. Because if you can tell an image has been doctored, even if you can't decipher it, you can at least now be aware that something is going on, and maybe you can watch who comes to the website.
Yeah.
Okay. So is everybody good on today's lecture?
Yeah.
Yeah.
Okay, what I'm going to do then is I'm going to disconnect the call and I'm going to call everybody back, because right now it's recording the whole call and I want to be able to just post the lecture, and I'll post it on YouTube, I'll post the Zoom link. I don't want to post our discussion of when are we free with our schedules. So I'm going to disconnect now and I'll call everybody back in a moment. Okay?
Okay.
Okay.
Okay.